by this time we have learned how to compute the magnetic fields for different conductors, for different geometries, and various situations associated with magnetic fields. Let's look at another situation where there is a conductor. Let's say this conductor is PQ. And let's say it's moving in a plane with a velocity v. To begin with, let's assume that the direction of this velocity is perpendicular to the length of the conductor PQ, right? Let's also assume that in this region there is presence of a uniform magnetic field going into the plane of the board, right? There is a uniform magnetic field going into the plane of the board, say. B, which goes into the plane of the board. Now, let's see how this conductor PQ responds to this motion in a uniform magnetic field, which to begin with is going into the plane of the board, right? First of all, realize that the conductor PQ has free charges, charges that could respond to forces. Now, if there are free charges here, think of a charge Q. The charge Q has a velocity v like this, synonymous with the conductor. The conductor is in a state of pure translation. The charge Q, let's say a certain free charge Q, will have a velocity same as that of the conductor. Now, because of this velocity, the charge Q will experience a force F, which is given by Q into V cross P. That's the force experienced by this charge, right? Now, if I think of a positive charge Q, then the direction of the force experienced by a positive charge would be the same as the direction of V cross B, right? Now let's look at the direction of V cross B. Realize that V is like this to the right, the velocity vector of this charge is to the right. There is B going into the plane of the board. There is B going into the plane of the board. So the direction of V cross B is like this. Do you realize that V cross B will be towards P? The vector V cross B would be towards P, right? V is this way, B is this way. So V cross B would be towards P. So all positive charges will experience a force in the direction of V cross B. So positive charges then would start to migrate towards P. So positive charges start to migrate towards P. What about negative charges? Negative charge, if Q were to be negative, it would experience a force F opposite to V cross B. You would then expect negative charges to migrate to the end Q of this conductor. So negative charges will migrate to the end Q of this conductor. Clear? Now, the charge, therefore, on this conductor from P to Q, there is a charge separation. There is a charge separation. More and more positive charges accumulating at P, more and more negative charges accumulating at Q. What does this mean? The implication of this is that this charge separation, positive charges accumulating at P, negative charges accumulating at Q, would result in an electric field from P to Q. It will result in an electric field from P to Q. Why? Why? Because if you think of a unit positive test charge placed here, it will experience repulsion from this and it will experience attraction towards this. Therefore, a unit positive charge would have a propensity to get attracted towards Q. Therefore, the direction of the electric field produced out of these induced charges accumulating at P and Q because of the motion of the conductor in a field results in an electric field E. results in an electric field EU. This is like an induced electric field. And the cause of this electric field is what? The cause of this electric field, fundamental cause of this electric field is motion of the conductor in a magnetic field, right? Now, as more and more positive charges accumulate at P, more and more negative charges accumulate at Q, the magnitude of this electric field will grow, right? Therefore, magnitude of the electric field grows with time, right? Therefore, at some instant, the free charges here, let's say, imagine a free charge Q between P and Q. That free charge will experience a force QE because of the electric field, will experience a force QE because of the electric field, and will experience a force Q into V cross B because of the magnetic field. If you imagine or conceive a charge Q, that charge Q will experience a force QE because of the electric field and a force Q into V cross B because of the magnetic field. And do you realize that the direction of QE is like this? V cross B is upwards. So Q into V cross B would be upwards for a positive charge. Q into V cross B would be upwards. Whereas QE would be downwards. Do you then realize that the force because of the electric field and the force because of the magnetic field are oppositely directed? However, this force does not change with time. Why? Because none of the entities here is changing with time. Whereas this force will begin to grow, right? Which means while this electric force is beginning to grow, after a while you would expect that the force because of the electric field would exactly cancel the force because of the magnetic field. Although the cause of this electric field is also the magnetic field, which manifests itself in a moving conductor as Q into E, right? So the fundamental cause of this is motion of the conductor in the magnetic field, right? So in any case, at some instant of time, the two will add up to 0. The two would add up to 0, and when the two add up to 0, then there would be no net force experienced by a charge Q in the conductor, right? There would be no further migration of charges from one end to the other. There would be equilibrium produced. The value of the electric field then, after a while, would be given by minus of V cross B. Minus of V cross B means the direction of the electric field will be opposite to the direction of V cross B because of this minus sign, and the magnitude of the electric field in equilibrium, the magnitude of the electric field in equilibrium would be B into V. Why? Because V and B are perpendicular to each other. V is like this, B is like this, V and B are perpendicular to each other. So magnitude of V cross B is V into B into sine 90 degrees. So eventually what transpires because of the motion of the conductor is an induced electric field E, obtained out of this charge separation because of the motion, and the electric field then between P and Q would have a magnitude B into V, Now, what does this mean? And the electric field would be directed, in this case, from P to Q. Now, what does this really mean? What it means is, the point P, which has surplus of positive charge, the point Q, which has surplus of negative charge, in equilibrium, there is an electric field from P to Q, given this set of conditions, and the value of the electric field is going to be B into V. The value of this electric field is going to be B into V. Now, what it really means is, what it really boils down to is the fact that this electric field between P and Q, and if L is the length of the conductor, then in the direction of the electric field, there is drop of potential. The potential that drops in the direction of an electric field would be E into the distance. That means between P and Q, what's the drop of potential? E into the length of the conductor. So the potential that drops between P and Q, the potential difference between P and Q, P across PQ is going to be E into L, is going to be E into L, yes or no, right? E into L means BVL, means BVL is what it reduces to, right? Now, the meaning of this statement is the potential difference across P and Q eventually being BVL should be interpreted as follows. When this conductor is in a state of motion, given these conditions, it behaves, this PQ will behave like a source of EMF the electrical equivalent of PQ. The electrical equivalent of PQ is a battery of EMF epsa equal to BVL. Because this battery would cause the potential difference between P and Q to be BVL. The positive terminal of the battery connected to P. Why? Because P is causing positive charges to reside and therefore is at a higher potential. So the positive terminal of the battery connected to P, the negative terminal of the battery connected to Q, causing P to be at a higher potential compared to Q. This is the EMF that is generated between P and Q. The important thing to realize is, so when this conductor is in motion, look at the direction of V cross B. The direction of V cross B would be the direction in which positive charges would accumulate, and that end would be at a higher potential compared to the other end. So this is the EMF generated between P and Q, and this EMF between P and Q is called motional EMF. Motional EMF. That's the EMF generated between P and Q, the motional EMF. Now, so if V is perpendicular to B, this is what happens. The motional EMF generated is going to be V cross B. Suppose the conductor was like this, PQ. In the earlier case, the velocity of the conductor was perpendicular to its length PQ and was also perpendicular to the magnetic field. Let's imagine a conductor once again moving in a magnetic field going into the plane of the board, uniform magnetic field going into the plane of the board, but let's say the conductor has a velocity V perpendicular to B but parallel to itself. The conductor is in a state of translation parallel to itself, V like this. All right. Let's see how this conductor would respond to this magnetic field. Let's see how this conductor would respond with this kind of a motion to a magnetic field into the plane of the board. B and V are still perpendicular to each other. Now, in this case, do you realize that if V is like this, V is like this, and B goes into the plane of the board, V like this, B goes into the plane of the board, so V cross B would be leftwards. V cross B would be leftwards. That means there is no component of V cross B along the length of the conductor. V cross B is lateral, sideways. This is V, this is B, so V cross B is sideways. There is no component of V cross B along the length of the conductor. That means if there is no component of V cross B along the length of the conductor, it really means that across the length there is no charge separation. There is no accumulation of charge at P and Q. And if there is no accumulation of charge at P and Q, there would be no electric field along the length of the conductor. If there is no electric field along the length of the conductor, the potential difference between P and Q is going to be 0. So, in a situation of this kind, there is no electrical implication of this conductor executing this kind of a motion in a magnetic field as shown, right? Now, what if B was, suppose V and B were parallel to each other. If this was a conductor PQ and say there was a uniform magnetic field B like this. There was a uniform magnetic field B like this, and the conductor was moving with a velocity V this way. What about this? What's the electrical implication of such a situation? What would be the electrical implication of such a situation? Nothing. Why? Because V is like this, V is parallel to B, so V cross B is going to be 0. So the charges, the free charges will experience no force. There would be no charge separation, no electric field, no motional EMF. So in this case, the motional EMF across PQ is going to be 0. In this case also, the motional EMF across PQ is going to be 0 if V was like this, right? Clear? Now, obviously, if V is along the length of the conductor, it does not result in motional EMF. If the conductor moves parallel to itself along its length, there would be no motional EMF generated across the ends of the conductor. Now, if there is a conductor PQ, and again there is a uniform magnetic field going into the plane of the board, uniform magnetic field going into the plane of the board, and the conductor has a velocity which is not perpendicular to PQ. Let's say has a velocity V like this, that makes an angle theta. This is the direction perpendicular to PQ, alright, and we have a velocity V. That means, again it's in a state of translation, but the velocity of the conductor is not perpendicular to its length, but is inclined to its length at a non-90 degrees or a non-zero angle. Now in this case, what we really do is we resolve V. We resolve V into a component, perpendicular component, which is V cos theta, and a parallel component, which is V sin theta. A perpendicular component, which is V cos theta, a parallel component, which is V sin theta. Now, like I told you, this parallel component of the velocity, that velocity which is parallel to PQ, will not participate in producing motional EMF. So this is passive. V parallel is passive, whereas V perpendicular does produce a motional EMF. What's a motional EMF produced by the perpendicular component of the velocity? B. Instead of V, we have V perpendicular into the length L of the conductor. Into the length L of the conductor. That's the motional EMF. B, V perpendicular into L. That's the motional EMF generated. Now, what's the direction? What's the sense or the polarities of the points P and Q? If V is like this, B is going into the plane of the board, then V cross B is towards P. So at P you would imagine positive charges to accumulate. At Q you would imagine negative charges to accumulate. So P would be at a higher potential compared to Q. So PQ acts as a battery of EMF given by B, V perpendicular into L, where the positive terminal of the battery would be connected to P and the negative terminal of the battery would be connected to Q. Such would be the result of a motion of a conductor having a velocity V as shown, right? Now, in the event, let's say the conductor is not straight. The conductor is not straight. Say the conductor is curved, okay, of complicated shape. This is the conductor of a very complicated shape, a conductor PQ, say. All right. And say this is PQ. And say this is the direction of the velocity V. This is the direction of the velocity V. All right. Like I told you, eventually, or let me, just to make life a little simpler, let me just do this. Let's say the conductor has a velocity V, which is perpendicular to PQ. All right. Then, and there is a magnetic field into the plane of the board. There is a uniform magnetic field into the plane of the board. Now, in order to calculate the EMF, see, this is the shape of the conductor. This is the shape of the conductor, right? The electric field, like I told you, right at the very onset, I told you the electric field generated between P and Q is going to be minus V cross B, isn't it? Minus V cross B is going to be the electric field that is generated. Okay. Now, if I go from P to Q, say, and I compute a E dot dl for every point between P and Q. For example, I take an intermediate point. The electric field is E at this point, say, given by minus V cross B. All right. The dl is along the tangent to the curve. dl would be along the tangent to the curve. E is the electric field at this point, right? Now, to go from this point to its neighboring point, what would be the potential drop? The potential difference is going to be minus E dot dl is going to be the change in potential, E dot dl, and I do this E dot dl for all points between P and Q. When I do this E dot dl for all points between P and Q, and I add up all of them, and I add up all the E dot dls, what would I get? The total potential difference between P and Q. I end up getting the total potential difference between P and Q. See, I take every point, I look at the E at that point. E is given by minus V cross B, as I have already shown to you, right? The electric field. And then I do a E dot dl, a E dot dl, a E dot dl, E dot dl for all points. When I do a E dot dl for all points, and I sum up all the E dot dls starting from P to Q, what would I get? I'll get the EMF across PQ, or the potential difference between points P and Q. So I end up getting the potential difference between P and Q on carrying out this operation, So now what does this mean? See, I can replace E by minus V cross B. So if I replace E by minus V cross B, so this will give me the motional EMF of this conductor. Complicated shape, motional EMF of this conductor. So then, replace E by minus V cross B. If I replace E by minus V cross B, I end up getting V cross B dot dl starting from P all the way to Q. Now, every element of this conductor has the same velocity V and is exposed to the same magnetic field B. So V cross B is the same for all the dls. V cross B will be the same for all the dls. So this V cross B will scoop out of the integral sign. So once it scoops out of the integral sign, I end up getting V cross B dot dl from P to Q, right? So when I essentially sum of all the dls from P to Q would be what? Sum of all the dls from P to Q. If I add up all the dls from P to Q, what would I get? If I add up all the dls from P to Q, this dl, this dl, this dl, then from polygon law of vectors, the vector sum of all these dls would be from polygon law of vectors, the vector PQ, isn't it? All the dls along with this PQ constitute an infinite sided polygon. The closing side of the polygon is PQ. So the vector sum of all the dls, as you can see, would be the straight vector PQ. That means this is like V cross B dot the vector sum of dls, which is the vector PQ. Starting from P to Q, This is just notional, saying that this summation is carried out from the initial point P to the final point Q. So I get V cross B dot PQ, which means when I say dot PQ, eventually if I'm getting V cross B dot PQ, it really means that the shape of the conductor does not matter. That means this conductor could have been replaced by one single conductor, straight conductor from P to Q, and I could carry out all the calculations that I carried out for a straight conductor PQ, instead of looking at this complicated curve, right? So which means if there was a complicated conduct shape in a state of translation exposed to a uniform magnetic field, then that thing could be replaced, that entity could be replaced by a single, this is the same as a single conductor PQ having a velocity V like this, same as that of the complicated conductor. And then the motional EMF would have a magnitude B into V into the length of PQ, straight length of PQ, which is L. That would be the motional EMF. So then it's really shape independent for a uniform magnetic field exposure in a state of translation. Yes or no? Right? Sounds good? Let's look at some real situations. So one thing that we've realized is that a moving conductor in a magnetic field is liable to a motional EMF, and we looked at some very basic situations related to that. Let's look at some more. Let me think of a very long current carrying wire, okay, and another finite conductor PQ at a distance x from this wire. Let me imagine a conductor PQ from this infinitely long current carrying wire, and let's say this PQ has a velocity V to the right, perpendicular to the conductor. PQ is parallel to this long conductor, and it has a velocity V perpendicular to PQ at a certain instant of time. Now, do you think PQ is exposed to a uniform magnetic field? Do you think every point between P and Q is exposed to the same magnetic field? Yes, because at a distance x, all points between P and Q are at the same distance x from this conductor. So the magnetic field exposure of PQ is going to be mu naught I divided by 2 pi x. That's a uniform magnetic field to which it is exposed. So this is, and do you realize that this is dl, this is r, so dl cross r is into, so the magnetic field B, mu naught I by 2 pi x, produced by this at all points between P and Q is going to be of magnitude mu naught I by 2 pi x, and it's going to go into the plane of the board. And again, if this is the case, and if the length of PQ is L, then what we've just learnt is that the motional EMF generated between P and Q is going to be BVL. That's going to be the motional EMF, where B is going to be mu naught I divided by 2 pi x into V into length L. That's going to be the motional EMF generated between P and Q. That's going to be the motional EMF. And again, if this is V and that's B, then V cross B is directed towards P. So P would be at a higher potential compared to Q. So PQ could be imagined to be equivalent to the following situation. This is plus, this is minus, this is PQ. Epsa then would be such. This would be the polarity assigned to P and Q. All right. Now, let me vary this situation. Let me think of a conductor in a state of translation but exposed to a non-uniform magnetic field. Let's look at that. Can I wipe this off? Right? Say, there is a conductor PQ like this. All right. Say there is a conductor PQ like this, and under the influence of the magnetic field produced by this infinitely long current carrying wire. Okay. And say this PQ is such that if you produce, it's going to be perpendicular to this. All right. Now, say this PQ has a velocity v this way. PQ has a velocity v perpendicular to PQ as shown. Would you then believe that different points between P and Q are at different distances from this conductor? Therefore, their exposure to magnetic field is different. PQ, therefore, the conductor PQ, therefore, is exposed to a non-uniform magnetic field. A non-uniform magnetic field. Now, suppose at the instant that we are imagining, say, this distance is A. This distance is A, right? And I think of a small element. This is a small element at a distance x from this infinitely long conductor. I think of a small element dx at a distance x from this infinitely long conductor. Now, this element then is exposed to a magnetic field. What's the magnetic field to which this is exposed? Mu naught I divided by 2 pi x, right? So, in this region, small region dx, the magnetic field produced by this infinitely long conductor is going to be mu naught I divided by 2 pi x. Mu naught I divided by 2 pi x, right? Clear? So, and what's the direction of this B? Into the plane. If dl is like this, r is like this, dl cross r is into. So, into the plane. In fact, by this time you've understood that all points to the right of this, if it's carrying a current upwards, would have field into the plane of the board. But different points between P and Q are at different distances x. Therefore, the magnitude of the magnetic field is going to be different for different points between P and Q. Now, so this is exposed to a magnetic field B going into. V is like this. V is like this. V is like this. B goes into. So, V cross B would be leftwards. V cross B. So, this small element dx that I have chosen, just to give you an accentuated view, this dx that I have chosen is such that V cross B would be like this. This is V upwards and B into the plane. So, V cross B would be leftwards. So, this point P would be at a higher potential compared to Q. So, that means this could be imagined to be a battery of this kind, minus plus, with EMF d epsilon equal to BV into dx. BV into dx. Dx is the length. Instead of L, you have dx. So, is going to be B into the velocity V into the length dx. Into the length dx. That's the d epsilon. Now, what we need to be doing is, we need to compute d epsilon for all dx's lying between P and Q. For all dx's lying between P and Q, we need to compute a d epsilon and carry out a scalar summation of all the d epsilons, right? So, this d epsilon is like a B. B could be replaced by mu naught I by 2 pi x. Into V into dx, right? That's the d epsilon produced by this chosen element at a distance x from the conductor. So, we need to select all the dx's starting from x equal to a x equal to a plus L. If L is the length of the conductor, then x varies from a to a plus L. So, we need to choose all the dx's from x equal to x equal to a plus L. Perform this d epsilon find out this d epsilon and then add all the d epsilons. So if we add all the d epsilons, sum of all of this starting from x equal to a to x equal to a plus L, right? And this integration will, as you can readily see, is mu naught IV by 2 pi log a plus L by a would be the total EMF generated, right? So this was the case where a conductor was exposed, this conductor PQ was exposed to a non-uniform B. Do you realize that this is a non-uniform B? A B that is varying from point to point along the length of the conductor. Then we choose our elements appropriately, compute the motional EMF contribution d epsa for every element between P and Q, and then add up all the d epsas. That's the idea behind computing the total motional EMF for a conductor exposed to a non-uniform B. Let's look at a conductor that's exposed to a uniform B, but different elements of this conductor have different velocities. Let's look at that case. Uniform B, but different velocities, right? Let's simulate a situation of this kind. Now, how could that be produced? Say there is a region of uniform B going into the plane of the board. There is a region of uniform B going into the plane. So we are trying to examine a conductor exposed now to a uniform B, but different points have different velocities. Now, imagine a conductor hinged at O. Imagine a conductor hinged at O. Imagine a conductor hinged at O, right, fixed at O, and is given an angular velocity omega, this conductor OP, which is fixed at O and is imparted an angular velocity omega, right? So now if it is imparted an angular, that means now it's in a state of pure rotation about O, right? Hinged at O means pure rotation about O, in a state of pure rotation with angular velocity omega, Now, let's say the length of the conductor is L. Let's say the length of this conductor is L. Do you realize that if this is OP with angular velocity omega, then if I look at, let's say, a certain element here, suppose I look at a certain element here at a distance x, if I look at a certain element here, right, all elements from O to P have the same angular velocity. Let me look at this element of length dx, which is almost like a point element. Then this element has a velocity perpendicular to OP, will have a velocity perpendicular to OP given by x omega. V is r omega, right? This element is executing circular motion centered at O and of radius x. So it will have a velocity perpendicular to its length and will be x omega. Clear? So now different elements from O to P are at different distances x, and therefore will have different velocities v. Now if they have different velocities, that means we have a velocity field from O to P, but exposed, let's say, to the same magnetic field B, uniform magnetic field going, say, into the plane of the board, into the plane of its motion, right? Now for this element, for this chosen element, which was like this was the chosen element, say PQ, just to give you a magnified view of PQ, right? This PQ has a velocity v like this, has a velocity v like this, has a length dx, the length of this PQ is dx, right? And the b to which this is exposed is going into the plane, the b is into, right? So if v is like this, b is like this, then v cross b would be what? Towards p or towards q? Towards q, towards q. V cross b, v is like this, b is like this, v is this way, b is into, then you realize v cross b would be towards q. So q would be a house for positive charges, p would be a house for negative charges, q would be at a higher potential compared to p. Therefore, this would serve as a seat of EMF with q being connected to the positive terminal of the battery, p being connected to the negative terminal of the battery. So q connected to the positive terminal, p connected to the negative terminal. The length of this conductor is, this element is dx, and b going into the plane of the board. So the source of EMF, this serves as a source of EMF d epsa this way. This element minus plus serves as a source of EMF d epsa like this. Yes or no? This element, okay, you know, I have chosen to call this P and Q. You might want to call this OA, because you know I've chosen these points as P and Q, so choose this point as A to avoid a clash. Okay. Now the EMF produced, the contribution of this element dx to the total EMF d epsa is going to be what? BVL, so B to which it's exposed, V into the length dx, BVL, right? So which is like B, and what's V? X omega into dx. That's the contribution made by this, right? The total contribution made by all elements starting from x equal to 0 to x equal to a would be sum of all of this, and all of these dx's are such that their positive terminals are towards a. So eventually A would be at a higher potential compared to O, right? The total EMF produced would be sum of all of this starting from x equal to 0 to x equal to the length of the conductor. Starting from x equal to 0 to x equal to the length of the conductor would be the total EMF produced from O to A, where A being at a higher potential compared to O. So this turns out to be half of B omega into L squared. Half of B omega into L squared is the EMF produced in a state of pure rotation with an angular velocity omega, and B being perpendicular to the plane of this circular motion of this conductor OA. Half B omega L squared in this case, very clearly, I repeat, this OA could be replaced by a conductor like this, where epsa is half of B omega L squared. Epsa would be half of B omega L squared this way. This is the electrical equivalent of this conductor in a state of pure rotation with angular velocity omega, different points subscribing to different values of the velocity because they are at different distances x from the hinge O, and the total EMF produced from O to A is going to be half B omega L squared. That is what happens, right? So then, now we have a case where uniform B but different velocities. Let's look at a case where B is also different and omega is, and velocities are also different. Let me look at a conductor which is exposed to a non-uniform magnetic field, and different points on the conductor are at different velocities, right? Let's look at that variation. So again, we can simulate a non-uniform magnetic field by an infinitely long conductor. This is an infinitely long conductor, I, right? And say this is a conductor, PQ. This is a conductor, PQ, hinged at P. Conductor hinged at P. And when produced, this PQ will be perpendicular to the conductor. This PQ will be perpendicular to the conductor. Now, if it's hinged at P, let me impart it an angular velocity omega, right? So now different elements would be at different distances from P, and therefore will have different velocities. So, and also since they are at different distances from this current carrying wire, they would be exposed to different magnetic fields. So here's a situation where the conductor has different velocities at different points and is exposed to different magnetic fields at different points. So both varying this time, right? Now if both are varying very clearly, let me look at a certain element. Let me look at a certain element, say Mn, at a distance x from the hinge, right? And let's say P is at a distance a from the current carrying wire, infinitely long current carrying wire, all right? And let's say this element is of length dx. Now, do you realize what would be the velocity of Mn? X omega, right? The velocity of Mn is going to be x omega, right? And different elements are at different x's from P, and therefore will have different velocities. So now for Mn, what is its distance from the current carrying wire? X plus a, right? So what's the magnetic field to which Mn is exposed? Mu naught I divided by 2 pi x plus a is the magnetic field to which it's exposed. Different elements therefore would be exposed to different magnetic field. Now let's look at the EMF contribution of Mn. The EMF contribution of Mn, d epsilon, is going to be the magnetic field B, which is into the plane of the board in this case, right? B into the velocity V into dx is the magnetic field, is the EMF contribution of this small element Mn. Now the polarities of Mn. See, if you look at Mn, it has a velocity V like this. It's exposed, its velocity V is like this. It's exposed to a magnetic field going into, so V cross B is towards M. So then M is at a higher potential compared to N, because V cross B would be towards M. Yes or no? That means this serves as a source of EMF of the following kind: minus, plus, this is d epsilon. Yes or no? I hope all of you understand this. This is V, this is B. V cross B would be towards M. V cross B would be towards M, right? So then the d epsilon produced would have this as the polarity, where the left would be at a higher potential compared to the right. So eventually what we need to do is sum up all the d epsilons where x runs from 0 to the length L of the conductor. Let's say the length L of the conductor, PQ. So x runs from 0 all the way to L. So the total EMF produced would be the sum of all of this. That's the motional EMF, where x runs from 0 to the length L, right? Now what we need to do is, we need to plug in the values of B. B is mu naught I by 2 pi x plus a. V is x omega into dx, where x runs from 0 to L. X runs from 0 to L, right? So we need to carry out this integration, and eventually, since for every dx the left end is at a higher potential compared to the right end, Therefore, eventually when I sum up all the d epsas, then the total epsa would be such that P would be at a higher potential compared to Q. And the potential difference between P and Q, that means the motional EMF generated across PQ would have a magnitude given by this integral. Yes or no? Right? Now, not difficult to obtain this integration. Pretty simple. See, things are constant. So many things are constant here. Mu naught I omega by 2 pi. Eventually, all that we need to do is x by x plus a dx. X runs from 0 to L, right? This is all that we need to integrate to get the total EMF from one end to the other. What we could do is, we could write this x as x plus a minus a, right? And then when I divide, this would be 1, and 1 by x plus a will give me log x plus a, so which is like mu naught I omega by 2 pi. This will give me L minus a log x plus a, where x runs from 0 to L. So this will give me log L plus a by a. Log L plus a by a is what I get when I integrate this. So this would be the motional EMF generated between P and Q. In the event we have a situation where the conductor is exposed to a non-uniform magnetic field and different elements could be at different velocities. I'm not saying that you need to mug up these formulas. All that I'm saying is you should know how to deal with the elements. You should not falter if you find B varying, V varying, or both varying. The ideas are very simple. 3 basic things and you're all set, right? You should know how to integrate and you're all set, right? You're doing good. So this gives us an idea of how to calculate the motional EMF for different situations, right? So we'll stop here and continue with this subsequently, right?